Good morning, guys. I'm glad that you guys made it. Sorry about that yesterday. Hopefully you guys were able to watch the video and did the quiz. It looks like a lot of you guys did the quiz yesterday, but also to you guys know there's a test that's due today. I do understand the pace, how everything is going. Like it's like almost every other day there's a test. It's unfortunate, but that's just how this course works. So you have to put in the time in order to be ready for the test, okay? I only see one person submitted the test that's due today. Let's go through the land acknowledgement and then we'll start. We acknowledge we're hosting the lands of Mississauga of Anishinaabe, the Haudenosaunee Confederacy, and the Wendat. We also recognizing the enduring presence of all First Nations, Métis, and Inuit people. Today's day 7. That means we technically have 10 more days, even though it says 19 days. We're done by day 17 as far as any new lessons. So if you think about it, we have a few more Fridays, but not to mention next week Monday is your midterm. So next week Monday we'll give you your midterm marks, and your marks are always going. Every time you do a quiz, I'll update it. I still have to mark the unit 1 test, get all those marks in, and then unit 2 test is due today. Okay. So let's get into it. We're gonna do the next unit, which is exponential functions. We're gonna talk about exponents, growth, and decay functions. And then there's a quiz. Okay. So basically the quiz is also due today, but you know, what's more important, your quiz or is it your test? Your test is more important than the quiz, so hopefully you can get the test done, which is on unit 2. Okay, so let us get into the content. I believe there's a video for this. Not sure. If not, doesn't matter, but we create the video. So yeah, there's no video for this, so that's fine. We create the video, and here we go. We're going to talk about exponential growth. So let me increase the screen. So I can see myself. So when we talk about exponential functions, we're talking about a function where the unknown variable, and that unknown variable is the independent variable, is the exponent. The independent variable is the exponent. When we talked about independent variables, right? Y is the dependent variable. Y is dependent on X. What X is will determine what Y is. And Y is not just the unknown, it's an exponent. Okay, so that's what we're looking at. We're looking at the unknown exponent, right? And this is like a growth chart. You can see it grows. That's what we see when something grows exponentially. You can say it grows exponentially because it starts out slow, then it rapidly increases. That's what we mean by exponential growth. So if we're talking about an example here, we can talk about bacteria, right? A typical bacteria grows so that it triples in number every day. So it triples in number every day. So the first day, say I start off with 100, but then after the first day, it jumps up to 300. Then 300 jumps up to 900. Then 900 jumps up to 2,700, 8,100. And before you know it, you get into like the billions. And if you think about COVID, that's how COVID basically spread. It spread exponentially, right? So that's what we're looking at. Okay. So what we're looking at is, if you guys remember from grade 9 about first differences, right? In grade 9, we talked about a linear function. We talked about the first difference being the same, right? In a linear function. Here, we're talking about how the first difference in an exponential function, first of all, we're talking about how the first difference and the second differences are basically, they're not the same. You can see 200, 600, the difference is not the same, but its growth is the same. So you go from 200 to 600, right? So it's the same multiplier, which is 3, because we're saying it's tripling for this one, right? And you do the second difference, it's the same thing, it's tripling. So when we talk about finite differences of a set data increased by a constant multiple, it is an exponential function. So the difference is increased by a constant multiple, and you can see the multiple is 3. Okay, and then basically we call that, letting some people in, we call that exponential relation or function. Okay, so here's a graph of that particular. You can see it grew exponentially. In 5 days, you're way up here, right? That's how kind of COVID grew, right? It started off with maybe really small, but then it spread quickly. So now, when you're given a chart, you may be asked to come up with the equation, right? And here is what you're going to do. Give me a second. Okay, so to come up with the equation, right? Now, when we talk about exponential functions, we have something called a standard equation. And I don't think, let me see, we're going to talk about it. Yeah, I guess we're going to talk about it. It's coming up. Okay, so in a standard equation, which I'm not going to just talk about just yet. Well, I guess I am going to talk about it. But this here is the future. I spell future right. This is the present. Okay, and this is like the growth factor. And then here, that is the time for growth. It actually tells you right here. Actually, I didn't even realize it's down here. So y is the future, the 100 is the present or the initial population. 3 is the growth factor, right? How much it grows. It grows like 3 every day. And then x is the time. Okay, so this is standard formula for exponential functions as far as trying to figure out what's the future amount based on my present amount. Okay, and it looks like we talk about it down here. So here we go. Standard equation, right? General equation. A is your initial amount or the present amount. B is your growth factor. And since it's a growth factor, it's greater than 1. When we talk about growth decay, it's less than 1. And then y is your future amount. X is the number of times it increases. And in this case, it increases every day, right? It's tripled every day, right? But sometimes we need to do calculations for x because we're not quite sure based on the question what we're using. just know that X is equal to total time divided by time it takes for one growth. So in this case, right, if we say, 5 days, okay, let me put it this way. If we want to know why, we want to know the future in, say, 10 days, right? So then what would happen was it would be our total time would be 10. Our total time is 10, right? And then I gotta let people in. People are just still coming in late anyways. Our total time is 10, but the time it takes for one growth is 1 day, right? 1 day it triples. So our exponent is not going to be 10 over 1. Our exponent is just going to be 10, right? Now, this part here could change. Say it took like 3 days to grow or to triple, then it'll be 10 over 3, okay? Because we want to know how much it is in 10 days, but we need to put in the denominator the growth rate, which is, in this case, it's 1 day, but in another example could be, say, 3 days, okay? So X is made up of total time divided by time it takes for one growth. You got to remember that, because that can throw you off depending on the question, okay? So here's the graph. You can see the change in Y. It's really drastic as you move along the X. My change in Y is 8. Initially, when I was down here, my change in Y was only 1, and I'm only changing from my X is only changing. It's only increasing by 1, right? So by the time we get to 10, it'd probably be like way off. It's already off the graph. It'd have been like somewhere crazy up into the billions or millions. Okay, now let's look at this example. Okay, your brother tells you a secret. Okay, I guess this is an example of a secret and how quick a rumor can spread. So, or a secret. Your brother tells you a secret. You see no harm in telling 2 of your friends. Okay, you told 2 friends. So after the second passing of the secret, 4 people now know, right? You know, your 2 friends know, and then your brother knows. So it's 4 people, right? If each of these friends now tells 2 new people after the third passing of the secret, 8 people will know. If this pattern of spreading the secret continues, how many people will know the secret after 10 passings? Okay, so each person's telling always 2 other people. That's basically, it's doubling, right? So when you are writing this out, so remember the formula? It's always A, and then you got B to the power of X, right? We said that this is the initial, this is the future, this is the growth rate, and this is time. It may not always be time. It could be, in this case, I'm going to say passing, right? Passing the secret, but it's not always time. But in this case, we'll say it's passing the secret. So my initial amount was 1. Only 1 person knew. Okay, and every person is telling 2 other people, so it's doubling, right? Again, so I gotta add people in. So it's doubling. And what we're saying is we're looking at what's the secret after 10, how many people know after 10 passings? So that's like our time, but it's just basically how often we want to find the secret, or how many people know the secret. So after 10 passings, we want to know how many people know the secret. So from there, we can calculate what would be the future amount of people that know the secret, okay? And that's sort of how we do that one. Okay, I'm gonna have to clear this. So if I scroll down, you see the calculations, right? After 10 people, or after 10 passings of the secret, not 10 people, after 10 passings of the secret, you're gonna have 1,024 people know that secret, right? So this is how rumor spreads, especially I'm saying rumor because rumor could be wrong, and we do this in you know, like we see in social media and news. Maybe news is wrong about someone. They say, oh, someone is dead, but then it's wrong. But before you know it, so many people know or have heard that announcement that it's spread like wildfire. Or in the internet, we call it went viral. And viral means it grew exponentially, right? So that's what we're talking about. This is what we're saying, that exponential. Here's another example. Insect colony. And these questions for exponents is always good for like insects and bacteria and, you know, things that grow exponentially. Most likely you're going to use this type of formula. Okay, so here, insect colony has a current population of 50. Its population doubles every 3 days. So now we got to do our X in a different way. It doubles every 3 days, not every day, but every 3 days. What is the population after 12 days? Okay, so you want to know your X. So your X is now going to be based off of, like we said before, number of days divided by the number, how many days it takes for it to grow. And when we say grow, in this case, how many days for the growth factor to take an effect. So the growth factor doubles every 3 days. So it'll be 12 divided by 3. So that would be your X. Okay. So we know our initial amount is 50. It's doubling. And when we do the math, after 12 days, you will have 800 of this bacteria. Sorry, of this insect. Okay. This stuff here I'm going to ignore because we're not learning log. Log comes into grade 12. Log is determining the exponent value using logs. But this is a grade 12 stuff here, so I'm not going to go through that. Okay, so here is so this was exponential growth when you have like a growth factor here, right? Now here is when you have an exponential growth, but we use percentages. Instead of a growth factor, we use percentages. So R is a percentage of a growth rate when we say rate. So this is the formula for that, right? X doesn't change, A doesn't change. The only thing is what's in the bracket changes, where you have 1 plus the percentage of growth, okay? So here, let's look at this example. In 2005, there were 285 Pittsburgh Penguin fans in Oakville. The number of fans increased by 75%. So the rate is 75%. 1 year, 75% per year after 2005. This is when Sidney Crosby was drafted. How many Crosby fans are now in Oakville in 2014? So every year, it said it increased every year. So our growth rate, and it's 75%. but the time is every year it's growing. Okay, so our X is going to be the difference between 2005 and 2014, which is 9 years. Okay, that's how we got 9 years. Now, our growth rate is 75%, so it's 0.75. I always write it as decimal. Our current amount is 285. So in the bracket, you're going to add 1 plus the rate. So now it's going to be 1.75. Your X is going to be 9. And here is now how many Penguin fans are in Oakville. It's a decimal, but obviously you don't have a decimal of a person, so you have to round up. That's why you have 43,872. Okay. And I believe we are done with the exponential growth. So now we're going to go and do the exponential decay. Let's go back. Here are worksheet questions, again, for no marks. It says there, not for marks. So you can work on it. You should work on it because that's how you're going to know. And here we're going to talk about decay. Again, worksheet, not for marks. So let's look at decay. So I can see decay is coming down. Let's look at that video. But it's no video. I mean, let's go through the worksheet. My bad, not the worksheet. The lesson. Okay, so now we're looking at exponential decay. And if you look inside this bracket, okay, you have a fraction. You have a number that's less than 1. When we're looking at growth, we're looking at numbers greater than 1, right? Even when we did the exponential rate, when we're using the R, it was 1 plus the decimal. So 1 plus that decimal gave you an answer greater than 1. Okay, when we're talking about the thing that I just showed you before, which was growth factor, and then you had growth rate. The stuff inside the bracket was greater than 1. In exponential decay, the number inside the bracket is less than 1. So in this case, it's a fraction, or it could be a decimal, but it's always less than 1. Okay. So you can see here, decay is less than 1. It's a fraction or even a decimal number. Everything else stays the same. The total time versus the time it takes for 1 decay. Okay. Here you can see something that we're looking at, which is more if you guys do chemistry, you would hear something called about half-life, right? Half-life calculation. So it's like how long it would take for a certain amount of material to be half the amount in the future. Okay. So in this case, you were looking at nuclear power plants using uranium-239 as a power source. So U-239 has a half-life of about 2 years. So that means in 2 years, whatever it started with, 2 years later, it would be half the amount. So you can see here, every 2 years, it's going down by half. Okay. So if you graph it, it's an exponential decay. Looks like this. It's going down by half every 2 years. So year 2, year 4, right, and then so on. So here's the equation for that, for this, right? So the equation would be, you're starting off with 1,000, and then it's a half-life. So that means in the bracket, it's going to be a half, and then you have an exponent. You don't know what it is, so X is the unknown. So now the question is, how much remains after 25 years? Well, you have to put X in terms of the time that you're looking at and the divided by the time it takes to do 1 decay. So 1 decay takes 2 years, right? So basically it'd be 25 divided by 2 gives you 12.5. So your exponent here is going to be 12.5, and then you plug it in. After 25 years, you will have 1726 milligrams. Okay, you start off at year 0, we start off with 1,000 milligrams. Now you're going to go all the way down to after 25 years, so basically nothing. Really, really small amount. Okay. Here's another example we're going to look at. Plutonium-239 has a half-life of 24 years. So after 24 years, it takes to do 1/2 for it. After 24 years, it will go down by half. Sorry for that, guys. Find the amount. Wow. Find the amount of 50 milligrams sample left after 35 years. Remember, it takes 24 years for 50 milligrams to go down to 25 milligrams, right? Because it says half-life, it takes 24 years. So half the amount of this would be 24 years. But we want to know how much is it in 35 years. So when you use the equation, your initial amount is 50, okay? Your growth decay is half because we're saying it's a half-life, so it's going to be half in there. X is now made up of what I'm looking at. I'm looking at for 35 years, and then the time it takes to do one decay. It takes 24 years to do one decay, so 35 divided by 24, that is my exponent. And then after 35 years, you're going to be left with 18.2 milligrams. So this is here when you just given like half-life. So you put the half in there, right? And that's your decay. In some cases, you're not doing half-life. Sometimes you're just doing it, it's going down by a percentage. So it's decaying by a certain amount. So if that's the case, you have a decay rate, which is R, and you basically use this equation. Okay, so here's an example where you can use growth rate, decay rate, when you're talking about something that depreciates. Like I buy a car, brand new car, and the value goes down every year. So this car costs 24,000. The value decreases 16% every year. So the decay rate is 16%. So I'm going to use this formula, 1 minus the decay rate. So it's going to be 1 minus 0.16, right? So now when I do that, in my bracket, you can see it's less than 1, right? It's less than 1. So as a result, that is my decay rate. And it's saying here, how much will the car be worth after 8 years? So my X is basically 8 because it's 8 years I'm looking at, and every year it goes down by 16%. My decay rate is 16% per year. So X is going to be 8 over 1, which is just 8. So as a result, my car is going to be worth, I spent $24,000. That's why car is not an investment. I spent $24,000. 8 years now, I'm only going to get barely, just under $6,000, right? Right. So cars, for the most part, don't hold its value. They're not an investment. That's just the life lesson right there. Okay. So now we're going to talk about this example where someone is taking Advil. Okay. So they take 400 milligrams of Advil. Each hour, the amount of Advil in the person's system decreases by 29%. So each hour, it's going down by 29%. How much Advil will be left in the person's body after 4 hours? So each hour is going by 29%. So my X is going to be 4, okay? Now, my rate is 0.29. What I'm going to have in the bracket is going to be 1 minus 0.29, and then you're going to get 0.71, okay? So now here is how much would be left in my body if I have 400 milligrams of Advil. After 4 hours, it's going to be 101.65 milligrams left in my body. Okay, we're not going to use logs because, again, logs is something that you do in grade 12. Okay, so here's a little bit of review of exponents, because you will be doing questions with exponents like this. Okay, so remember the laws of exponents. If I'm multiplying all the bases and they're all the same, I just add the exponent. So what I'm doing here is I'm adding -2 and -3 and then +4. So -2, -3 is -5, +4 is -1. Okay, so x to the power of -1. Also, we know that when it's x to the power of a negative exponent, it's just basically 1 over x to that exponent. Okay, and we don't put the exponent here of 1 because you never put anything to the power of 1, right? We assume you just don't do that. Okay, now with this one here, again, I'm dividing, right? So if I'm dividing, that means I'm subtracting the exponents. So this case here would be, if I'm looking at each term, right, each variable, so a to the power of 2, right, divided by a to the -1. So what happens is, let me write it on the screen because I feel like you guys are gonna like not get that if I don't write it. Right? So a to the power of 2 divided by, hey, come on, pen. Okay, I'm having difficulties. Come on. Oh wow, maybe my battery's dying. Okay, so what happens is when I have that, that's the same thing as saying a to the power of 2 minus 1. So I'm going to have a to the power of 3. Okay, that's how they got that. Okay, because when you're dividing, you subtract the exponents. Okay, and here I have a negative exponent, so a negative becomes a positive, right? So if I have b, I'm going to do b, right, over that. That's like saying b to the power of -3 minus 2. So then b becomes to the -5. Okay, that's how I got that. And then obviously when you write it down, you want b to be in the bottom. So it's going to be a to the power of 3 divided by b to the power of 5. Okay, so that's how you do that. Okay, and then this one here is sort of the same thing. You're going to apply that rule, right? So this rule means I'm going to multiply each of these by -3, each of these exponents. Okay, each of these terms, I should say, even the coefficient gets multiplied, not multiplied, but it gets to the power of -3. So here, -2 times -3 gives you 6, right? That's how we got that 6, because it's a positive 6. Okay, and then -3 times 3 gives you -9, and then 2 to the power of -3, that's what we get there. Okay, and also too, you know that you can't have a -3. You can have a negative exponent, but we always deal with positive exponents, so you're going to write it as 2 to the power of 3 in the denominator. Same thing with this, u to the power of 9 in the denominator, and as a result, this is what you get. Okay, let me clear that. Here are more examples. Okay. So this is, again, this is a lot of exponent rules you should know, right? So you have something like this. Okay, people are coming in late, or maybe they're losing the Wi-Fi, maybe. Okay, so this one here, this is just saying I'm going to do the reciprocal, right? So 3/1, same thing as saying 3. This one here, I'm going to do the reciprocal, 8/27. And then when you have a negative here, you have to give it to somebody. You have to give it either to the 27 or to the 8. In this case, we gave it to the 8. It doesn't really matter because we're going to apply this exponent to the fraction, and this becomes -8 times -8 gives you 64, and then 27 times 27 gives you 729. Okay. And I believe that is it for the lessons today. Let me double check. Yeah, that's it for the lessons today. Okay. I'm gonna go back to home. All we're doing is exponents and then growth and decay. And then you got a quiz. So it's a light day because you have this. You still have your test that's due today. Okay. So I will end this a little bit early. That way you guys can have time to go ahead and do the things you need to do today. Okay, I'll post this video. And again, guys, just continue to working hard. You guys are doing well. And just continue. Okay. So guys, have a good rest of the day, and I will see you tomorrow. Take care. Bye.